Okay. Let me share my screen. One second, y'all. Just want to test this out. Okay. Load this up. I'm going to actually go ahead and I'm going to put the link to these slides and the code in the Zoom chat. So if y'all want to check those out. We have all the code hosted on our repo. So if y'all want to download that and play around with it, you're welcome to. Okay. Okay, welcome everybody. My name is Matthew Cooper. I'm one of the instructors here at PDS Code Guild, and happy today to be talking to y'all about big O notation analysis of algorithms with Python. It's a long title, so let's get into it. Okay, so just a quick overview of the presentation. I'm going to talk about the definition of big O and its mathematical basis. We're going to talk about some testing methodology because I want to give you all some fancy charts to look at, and then we'll take a look at examples of big O, just linear search, binary search, traveling salesperson. You all have heard of those before. We're going to look at some sorting algorithms, and we'll look at some data structures. So this is going to be like very code heavy. We're going to look at a lot of examples rather than being like really theory heavy. Because I was trying to think about you know, what types of things people are going to find on their programming interviews, because that's really what I want to prepare you all for. And then there's a link there to our code repository if y'all want to check that out. Okay, so what is big O notation? Big O is used to describe the complexity of algorithm, especially for large inputs where concerns about efficiency become significant. So, you know, if you have a very small data set, it doesn't really matter if you run an inefficient algorithm on it because it's not going to take much time. And we also want to characterize the complexity of an algorithm independent of any particular hardware configuration, programming language, or insignificant aspects of the implementation. Because, you know, different people have different machines. You know, you could have a CPU that's twice as fast as another, and it'll run an algorithm twice as fast, but that doesn't help us talk about the algorithm itself. And also, like, even on your own machine, if you're running like multiple applications in the background, that could actually still slow down the algorithm as well. So there's a lot of parts about the runtime of an algorithm that we want to kind of abstract away. And there's kind of like, there's two really forms of complexity that big O can capture. So the first is time complexity. So that's a relationship between the size of the input and the number of steps needed to solve the problem. And that's what we're going to talk about throughout this presentation. But then there's also space complexity. So space complexity is a relationship between the size of the input and the amount of memory required. Memory is so cheap these days, we don't really care so much about space complexity. But it is really, can everybody mute themselves, please? Go through mute people. Thanks. It is really easy to come up with an algorithm that, which basically takes several times the age of the universe to run, even on really modern CPUs. So time complexity is generally more important. So a really quick example. Let's look at this algorithm to calculate the average of a list of numbers. So you can see here, we've got total equals 0, I equals 0. We're looping, summing up all the numbers in the list. And then we're calculating the average and then returning the average. So, we got a quick little list comprehension here, which will just generate a list of 10 numbers, and then we call the average function. So if we wanted to, we could actually figure out the cost of each individual operation in this entire algorithm. So first there's a function call, then we calculate the cost. We have the cost of an assignment, we got a comparison, as well as another function call. And then we've got a sum, an assignment, also a list access, and then a sum and another assignment. So you could actually like figure out the cost of each of these operations, and then figure out a function that would actually give you the runtime for the algorithm based on n, which is the size of the input. So this is a really complicated formula, and obviously it's going to vary between languages. It's going to vary between computers. So we want to kind of abstract away all those C terms, and we just want to really talk about how this function grows as a function of n, which is the size of the input. So in big O notation, we would say this algorithm is O of n. Okay, wait. Okay. So let's talk about the mathematical basis of big O, because it does have a pretty heavy mathematical basis. So a function f of n is said to be O of g of n if there exists a c and an n naught such that f of n is less than or equal to g of n, c times g of n for all n greater than n naught. So basically, can we find a function which is always greater than that other function? So f of n here is our runtime, and then g of n is how we're trying to characterize that runtime in big O. So say our runtime f of n is 6n squared plus 3n plus 4. We could figure out a c and an n naught, which is always greater than that function. So so let's say c is 7 and n naught is 4. And you can see in this chart that 7n squared is actually greater than 6n squared plus 3n plus 4 for all n greater than 4. So that's why we can say 6n squared plus 3n plus 4 is O of n squared. And keep in mind too that the g of n, it's an upper bound of f of n. So technically, if f of n is O of n squared, it's also O of 2 to the n O of n factorial. So normally you only see the lowest term, but just keep in mind that it is an upper bound. Let me see if I can close this thing. Oh boy. Nope. Can I move it? Can you guys see this, by the way? I get so confused between this and Zoom. I'm guessing you can. Somewhat, Sherry said you can. Okay, well, I'll try not to move my mouse as much. I don't know. Okay, so looking at the different complexities. So this is kind of a nice big chart listing out some of the major complexities. So O of n factorial is probably the worst there in red. It just explodes with n. O of 2 to the n's really bad still. O of n squared is pretty bad. O of n log n is kind of getting into good territory. And O of n, O of log n, and O of 1 are probably our best bets. So if you have an O of n factorial algorithm, it's very easy to come up with an input that will take, billions of years to complete, basically. So the complexity of an algorithm can mean the difference between minutes and millennia, basically. And always keep in mind, though, with this also, algorithms with greater complexity may run faster than those with less in practice. It really, it depends on the particulars of the implementation. We try to abstract those away to better characterize the algorithm itself, but you could have theoretically an O of 1 that actually runs faster. Sorry, you could have an O of 1 that actually runs slower than an O of n factorial for certain inputs, if it's a really big O of 1. Okay. So I implemented a little bit of test code because I wanted to generate some fancy charts. And it's a little bit much. I hope you all are familiar with Python. Basically, we're using a global variable to keep track of the number of steps the algorithm is going to take. And we're going to run the algorithm on a bunch of different input sizes. And we're going to do a bunch of trials for a given input size to average out the, some noise that'll be in the number of steps. Because the number of steps an algorithm takes for a given input size could vary dramatically. So you can see here we got some X and Y values. We're looping over our different list sizes. And then this whole inner loop here, we're running a bunch of trials. So say we run 10 trials for a list size of length 5. We then, for each of those trials, we generate a list here with the list comprehension. We invoke our algorithm, and then we sum up the number of steps that algorithm took to solve that particular list. And then we just calculate the average, and then we add our X and Y values to our chart. So I hope that makes sense. Basically, we're iterating over a range of different list sizes, and we want to know for a given n how many steps it's going to take on average. So we try it a whole bunch of times and then average out the results. So here, going back to our average algorithm, we're iterating over the our list of numbers, and you can see here we actually increment our counter, and then we invoke this little we invoke our chart complexity algorithm, which will actually run all those steps. So here we're running 100 trials, and n-min is 1, n-max is 50, and n-step is 1. So we're going to basically test all list sizes from 1 to 250, and we're going to try each list size 100 times and take the average. And you can see here, the counter is always going to be the same for a given list size. So we actually have a nice flat line. And you can see it's a line, it's a linear relationship, right? So that clearly shows that this algorithm is O of n, because the runtime is basically directly proportional to the size of the input. So there's a cat just to fill up some space. So we're going to go through some quick examples of different big O examples that you might see out there in the wild. So first one, a random element function. This is O of 1, right? Because no matter the size of our list input, we're only gonna take one step. Generating a random numbers, it doesn't require any more steps. Using an index to access a list element doesn't require any more steps. So this has basically a constant runtime. Linear search. So here we are iterating over a list of numbers, and we're looking for a particular number. We want the index. So we're iterating through, we're incrementing our counter, and if the given number is equal to our target number, then we return the index. And you can see why this is a little bit noisy, right? Because where we find that target number in the list will determine how many steps we take. But it is still a linear relationship, because on average, we'll have to take n over 2 steps. N over 2 is still O of n. Binary search. So this is kind of like a big improvement on linear search. We basically start with the whole list as our search range. We pick out a middle number, and if the middle number is less than our target number, then we repeat the search in the lower half. If it's greater than our target, we repeat the search in the upper half. And if it is our target, then we've basically finished. So here you can see in white, that's our search range. The yellow is our target number, or sorry, the yellow is our middle number that we're picking out. So the first iteration, we pick out 11. Well, sorry, we're looking for 17 in this array of 10 numbers. So the middle number is 11. 17 is greater than 11. So we basically repeat the search in the upper half. And then we pick out 19. 19 is greater than 17. So we repeat the search in this lower half. And then we do find 13 is our middle number, whatever the middle is for two numbers. And and that's less than 17. So then we search in the upper half and then we finally find 17. So in code, we basically have the same parameters as our linear search. We have an array of numbers and we have our target number. We start with the low index and our high index, right? That's the lowest valid index and the highest valid index. And we loop while the low is less than the high. We increment our counter, calculate the index of the middle element. And then if the middle element's greater than our target, we want to look in the lower half. So we shift the high down to the middle. If the middle is less than the target, then we shift we want to search in the upper half. So we shift the low up to the middle. And otherwise we return the middle because then the nums of middle is equal to our target. So you can see here this curve. It's very pretty. That's a logarithmic curve. And you can see even for 200 numbers, this is barely getting above 5. So compare that to the curve for linear search, where for 250, we're already at 160 on average. So 160 steps versus 5 steps, it's a major difference. So even though you might say that this is more complex in terms of code, the algorithmic complexity is actually a lot less. It has a much faster runtime for a given input. Cool. So some more examples. Find pairs, O of n squared. So here we have an array of numbers and a target number, and we want to know, are there any two numbers in our list that sum to the target number? So we iterate over our list. We have to iterate over our list again to compare each number to every other element, each number to each other number. We increment the counter. We check if those two numbers are equal to our target, and if it is, we return a list containing both of them. So you can see why this is O of n squared, because we have a loop within a loop. Whenever you have a for loop and a for loop, you're always looking at O of n squared. And you can see that in the chart, right? For 100 numbers, we're already up to 2,500 steps. So that function kind of explodes. Another n squared operation is figuring out the common elements between two lists. So we start with an empty output list. We iterate over all the numbers in the first list. And then for each of those numbers, we have to iterate through all the numbers in the second list. And if they're equal, then we put them in our output list. So trying to find the common elements between two lists is an O of n squared operation as well. And you can see there it really explodes. At 100, it's already at 2,500 steps. I just want to take a note here to remind you all to watch out for implicit loops. I could definitely see this being like a tricky interview question. This is the same algorithm, but we're using the in operator. So here we're looping over all the numbers, and then we're just checking if the number is in the second list, add it to our output list. If you were just glancing at this, you might not realize that implicitly Python's doing a for loop to figure out if this number's in this list. So, so just watch out for implicit loops. Another quick example, Fibonacci. If you all know the Fibonacci sequence, each number is equal to the sum of the last two numbers. So the iterative solution, we just have to loop up to n. So that's a linear relationship. So iterative Fibonacci is O of n, right? We just have two trailing numbers, A and B, and then we calculate C is the sum of A and B, and then we just basically shift those two numbers down. So A becomes B and B becomes C, and then we just repeat the process n times. Recursive Fibonacci, you might see this one. This is pretty well known for an 2 to the n operation. We basically have our recursive algorithms. You always have the base case and then the recursive call. So the base case here is if n is 0 or n is 1, we return 1. Otherwise, we return, we call the function twice in recurse, and then and that just really explodes, right? Because you can see in this tree here, f of 5, to know f of 5, we need to call f of 4 and f of 3. To know f of 4, we need to know f of 3 and f of 2. To know f of 3, we need to know f of 2 and f of 1. And then finally, f of 1 and f of 0 can return. So this is this is called an exponential relationship, or an exponential time. So you can see it already gets up to, just for the number 23 or so, it's already at 140,000. So it gets really big really fast. Okay, and this is probably one of the more complex examples. I just wanted to show it to y'all because traveling salesman is it's a really common algorithm out there. It's well known for being difficult to solve. Basically, the problem is we want to visit n cities, and we have the distance we have n cities, and we have a bunch of distances between them, and we want to find the shortest path that visits each city exactly once and returns to the first city. So there are fancier ways to cutting down on the complexity of this, but the simplest approach is really just to try all possibilities. And if y'all remember, if y'all ever studied combinatorics, if you have like n elements, there's n factorial possible ways of rearranging them, right? Because if you think of the first element could be one of any n elements, the second could be n minus 1 elements, the third could be n minus 2 elements, and so on. So you get that n times n minus 1 times n minus 2 times n minus 3. So n factorial possible ways of rearranging the elements of a list. And that's what we got to work with here. So I actually found some code online. There's someone that did this in 10 lines of code. It was a mess, though. I expanded it to 25 and made it a little bit clearer. But basically, here we're generating a list of tuples, each with an x and y coordinate. I used iter-tools just to generate all the permutations. It is a little bit complex to actually implement that if you want to do it yourself. Anyway, and then we just figure out all the path lengths. We calculate we just loop over each path and then loop over each city within the path. And then sum up all the path lengths, the distances between each city. And then add finally the distance between the end city and the start city, find out the minimum path, and then chart it. So yeah, traveling salesman, it's ordinarily it's O of n factorial. There are some algorithms that can cut that down a little bit. Cool, and that's the chart that it generates. Nice one, it's a nice one. And you can see here on the right, we have the actual curve. And for just 8 cities, we're already up to 3 million possible combinations. So factorial just really explodes. Okay, so moving right along. Are we on time? Oh boy. So let's talk about some sorting algorithms. So I want to look at BOGO sort, bubble sort, selection sort, and quick sort. These are all pretty well known. So BOGO sort's really a dumb algorithm. It's basically we generate random possible combinations of an array of numbers until we happen to find the one that's actually sorted. Again, from traveling salesman, there are n factorial possible ways of rearranging the elements of a list. And we also have to check if it's sorted, which is an O of n operation. So that's why you get the O of n times n factorial, because on average, this infinite loop will go n factorial times. And then inside here, we actually have to loop n times to check if it's sorted. Anyway, oh, and we also need to take n steps to shuffle it. So this is called the Fisher-Yates shuffle algorithm. Basically, we iterate through the indices of the list. We pick a random other index, and then we swap the elements of those 2 indices. And then to check if it's sorted, we just set a flag as sorted as true. If we loop through all the numbers in the list, if a number is greater than the next number, then it's not sorted, right? And we assume it's ascending order. So if any pair is out of order, then the whole thing is out of order. We set this flag to false and we break. Got some questions coming in. So I just want to address these really fast since we got a little bit of time. How do we find the runtime of an implicit loop? Should we always assume they're O of N's? O of N? It really depends. It really depends. You know, obviously, you could use some built-in functions, like we saw the traveling salesman. This itertools.permutations, that's an O of N factorial call. So you just kind of have to know what algorithm, the complexity of the algorithm that you're calling. And someone asked, is time complexity the same algorithm, different language, always the same? Yes, it is. So the same algorithm in different languages will actually have the same complexity. That's the whole point of the big O notation, is that we can talk about an algorithm without talking about the particular machine it's running on or the particular language that it's implemented in. Okay. So yeah, anyway, so this function really explodes. You can see here, just for 7 numbers, we're already at 35,000 steps, which is pretty huge. So that's a terrible algorithm. Bubble sort, this is a really common one just because it's simple. Basically, you can already see right off the bat it's kind of an O of N squared operation because we have a loop within a loop. So the outer loop's going to go over the full range of numbers. The inner loop's just going up to it's going to go one less from the end for every iteration of the outer loop. And we're swapping each number to the next number if it's out of order. So here's a little visualization. I know that's a little hard to follow, but basically we just always look at pairs of numbers. So the first run of the outer loop, we're going to go over the full range of numbers. And then we just keep swapping pairs. And then we know that the last one's always in place. So we can actually iterate one less the next time. And again, it's called bubble sort because we're kind of bubbling up the numbers. Okay, next, what is the chart complexity dot counter counting in relation to the axes on the graph? So someone asked, what is this chart complexity dot counter? Basically, the chart complexity dot counter it's basically the x-axis. Well, sorry, no, the chart complexity dot counter it's the y-axis. N here is it's the size of the input, the size of the list that we generate. And then for a given size input, we're running the algorithm and figuring out how many steps the algorithm takes. And we're counting that up using that counter. So that's the y-axis. So x is the size of the input, and then y is the number of steps that we're taking. And could everybody make sure that they mute themselves? Thanks. Okay. And don't make me go through the list of 50 people. Okay. Okay, so moving on. So selection sort, it's O of N squared. So selection sort's another pretty intuitive algorithm. Basically, we just loop through our list of numbers, and then we figure out what number should be. We basically, for the first number, we want the lowest number, right? And then the second number, we want the second lowest number, and the third number, we want the third lowest number. So I is going to go over our range of indices, and for a given index, we want to know what number should be there. So we iterate over the rest of the range, right? J in range I plus 1. And then we basically check, we have this min index, and we check if the number that we're looking at in the rest of the list is less than our running minimum. And if it is, then we assign that index to our minimum index. So we're basically just figuring out the lowest number in the rest of the list. And then down here on line 13, we're putting that lowest number in its proper place in the list. So it's a little bit more intuitive than bubble sort, I think. but it is still an O of n squared operation, right? Because we have a loop within a loop. Okay. Quicksort, this is going to be a bit of a doozy. I just want to give you kind of a quick overview and talk about the complexity. Quicksort's it's a fairly complex algorithm, but it has a really great running time. Basically, what we do is we pick a pivot, and then we move elements that are less. We move elements to the left and right depending on whether they're less than the pivot or greater than the pivot. So here our pivot is 4, and we can basically iterate through moving. We move the 7 to the right of the 4. We move the 5 to the right of the 4. Move the 9 to the right of the 4. So, and then we just loop down. So that's what the partition out part of this algorithm does. Is it just moves elements to either side of the pivot, and then we just basically repeat the process on each section. So here we move the 4 into the center, and then we basically recurse, and we call the algorithm again, and then we do the same operation on each of the sublists. So the first sublist is 3 through 2 here, and the second sublist is 5 through 7. And then each of those sublists get sorted. They have their own pivot. So anyway, the partition algorithm is what moves the elements on either side of the pivot. And then the quicksort part is what actually recurses. So this is the implementation in Python. And you can see it is actually n log n. So the n part comes from the partition, and the log n comes from the quicksort recursives. So this kind of looks like binary search, right? You have a low and a high index. So every iteration, you're basically dividing your list in 2. So that's where the log n comes from. And then the partition is an n operation because you're iterating over this range of numbers. So that's why it comes out to be n log n. And you can see already, like for even a list size of 100, we're only at 600 steps. Whereas, selection sort for 100, we were already at 5,000 about. So it is basically 10 times faster for a list that size. Someone asked, is the quicksort algorithm a map reduce function? No, I think those are pretty different things. Okay. Okay, so where are we on time? Let me check this out. I want to leave some time for questions. So let's look at some data structures. So we're going to look at array list, stack, linked list, hash table, and a binary search tree. And again, there's another cute cat for you. So an array, it's basically a continuous block of memory. You don't really have access to arrays directly in Python, so we'll just kind of have to use our imagination a little bit. But access only requires a bit of arithmetic, so it's O of 1. If you ever use C and C++, you're well aware of the arithmetic involved in accessing the element of an array. Basically, you have a block of memory at a given memory address. So this array actually starts at memory address 248,350. And then each of our elements in the array is 4 bytes. So you can actually figure out, if you had the index, you could figure out the memory address of any element. Because they'll each be 4 bytes, the starting location, so you can just do a little bit of a multiplication. This is why arrays always start at index 0, is because of how they were originally implemented in C and C++. So this is kind of the formula for calculating the address of an element. So the address of the element is equal to the address of the array plus the size of the element times the index. So the size of so a little quick example here, if our letters are HELLO as they are up here, and we want to figure out what is the value at index 4, we can just add the start of the array plus 4, which is the size of the element, times 4, which is our index, which will give us the index in memory of the 4th element, the element with index 4. So yeah, it's basically an O of 1 operation, right? Because all we have to do is a little bit of math, and then we can go get the element at that index. But arrays come with a downside, is that appending and removing requires reallocating the entire array. Because you can't always be sure that if you allocate a huge block of memory, that any numbers after that or before that, or any memory after that or before that is empty. So you always have to, if you want to add something to the end, or you want to insert something into the middle, or delete something from the middle, you basically have to reallocate the entire array. So this is kind of what it would look like in Python. Again, lists use arrays under the hood, but they're not exactly arrays because they have those append methods. We'll talk about that in a little bit. But yeah, basically access constant time operation. So that you just use the index to access the index into the list of elements, and then appending. Here we create a second array. Using array. We create a second list with a bunch of nuns inside, and it's one more than the length of the original. We copy over the data, and then we insert the value into the end of that list, and then we replace the original list with a new one. Kind of similarly with remove, we create a new temporary list with one less of the length, and then we iterate over all our elements and then copy them over to the temp list, and then assign the temp list to our old list. So you can see why that's an O of n operation, is because you have to iterate over that list of numbers. And then things like finding, if you wanted to find the index of an element, you have to iterate over all the numbers basically. So that's an O of n operation as well. An array list it's a little bit of an improvement over arrays. This is basically what Python lists are under the hood. They basically keep a whole bunch of empty slots, so you don't have to reallocate every time you add and remove things. You can see here with the append, we keep track of a separate length property. So initially we have 10 empty slots and have a length of 0. And then when we append things, we can check if the current length is less than our real length. And if it is, then we can just insert it at the end and increment our length. But if it's not, what we're going to do is we're going to reallocate a new list like we did before, but we're going to double the length. So it gets twice as big every time we hit the limit. So that actually cuts back on the number of times we have to resize the whole list. So that's what Python lists use under the hood. Yeah, for anybody asking, the video it is being recorded, so y'all can watch later. So if you're scribbling down notes, don't worry so much. Let's look at stacks. So a stack is a data structure. It resembles a stack of plates. You can add and remove things from the top, but you can't remove things from the bottom or anything else. There's lots of different ways of implementing stacks. You can do them with lists or not. Here we're going to implement a stack using a bunch of links between nodes. So each node stores both the value and a reference to the next node. So you can see here we have a stack and we're doing a push operation. So push is adding an element to the top, and then pop is removing elements from the top. So this is also called a LIFO data structure, last in, first out, because the last element that you added is actually the first to come out of it. And then again, we're going to implement this with nodes. So each node is going to contain both the value and a reference to the next node. So what that'll look like in Python, these nodes, right? There's our initializer. It's just got the value in the next node, 2 properties. And then our stack, we have the initializer. We initialize the root to none. Our push operation, we basically replace the old root with a new node. And that new node's value is equal to the value that we're pushing in. And the next node of the new node is the old root. So a little bit confusing, but basically we're taking, you have the root node, and then you're just inserting a new node in front of it and making the next node of this new node equal to the root node. So you can sort of imagine here, if we were inserting a new value, we would, say we were adding the number 6, it would have the value 6, and then the next node would be the old root. And you can see these are all O of 1 operations, right? None of them depend on the actual size of the list or the number of nodes that we have. So stacks are used in a lot of different places, particularly in function calls. Y'all probably know Stack Overflow. So Stack Overflow is the error that you get if you make too many function calls and you recurse too much. You'll run out of space for your stack. A linked list is used a lot like a stack. We have, again, just a bunch of nodes and a reference to the next node. Except here, we're supporting other operations besides push, pop, and peek. So append, we want to add it to the end and not the front. So when we're appending a value, we're checking if the root's none. If the root's none, then we just create a new node for the root. But if it's not, we have to loop through until we get to the last node, and then we can create a new node for the next node of the last node. So right, node equals self.root, and then we're saying, well, node.next is not none, node equals node.next. So basically, while the node's next node is not none, we're replacing the node with the next node. So we're just kind of stepping through our linked list. And then finally, when we get to the last one, we can say the next node of this node is equal to a new node with the value that the user entered. And then similarly, access, we have to iterate through the nodes again. We want to access the value at a given index. So we assigned self.root to a node. We're looping while the node's not none. We're checking if the index is 0, and if it is, we return the node.value. Otherwise, we decrement the index. So every step, we decrement the index 1, and eventually we end up with an index of 0, and we'll return the node's value. And if we run out of nodes, we'll just return none. So you can see that this is these are O of n operations, right? Because for n nodes, we still have to loop n times. And again, these are some more operations on linked lists. Here we're calculating the length, setting a counter to 0. Again, we're starting with a node. We're looping while the node's not none, and we're incrementing a counter. So that'll give us the length. Removing is a little bit technical. I don't know if I'll waste time getting into it, but basically we loop through until we find a node with the given value. And then we actually, this is probably the ugliest line of code here on line 38. Node.next is equal to node.next.next. That's how you erase a node in a linked list, right? So you have the node, it has a next node, and you're assigning that to the next node of the next node. So that'll actually remove a node from the chain. Again, O of n operation. We're trying to find a node with a given value to return its index. It's also an n operation. So remove, find, and length are all O of n. And so we're access and append. Okay, so just a couple more data structures, and maybe we can open up some questions. So a hash table uses what's called a hashing algorithm. It can basically turn a key into an integer, and then you can use that integer as an index into a very large array. So Python dictionaries actually use hash tables behind the scenes, and that's one of the reasons you can't use a mutable type as the hash. It has to be an immutable type in order to be used on a hash algorithm. And hash tables are nice because insert, access, delete, and search are all O of 1. So that hash function might actually be pretty complicated. And I've seen a lot of really complex hash functions out there. So it's a big O of 1, but it is still a constant time operation. So it's good if you have a lot of data. This is my poor attempt at a hash table in Python. But basically, we start out with a list of a bunch of nuns, 100 nuns. And then we use our hashing algorithm. Say we want to insert a key value pair. We basically run the key through our hashing algorithm, and then we use that hash as the index into our list, and then we assign a value at that index. So it's very similar for access. We run the key through our hashing algorithm, and then we assign we return the value at that hash. So our hashing algorithm here is relatively simple. We basically just sum up or char here, right? That's going to convert a character into the ASCII value of that character, and then we just multiply that by a number, and then we just sum all those up, and then we can mod by the number of slots that we have to wrap it back around to be in range. There's lots of mathematics behind what constitutes a good hashing algorithm. This is a pretty poor one relatively, but it is simple to understand at least. Certain properties of our hashing algorithm, we don't want to have collisions. So a collision is when two different strings will hash to the same number. And if that happens, you'll try to insert two values in the same spot in our hash table. So you want strings that are even slightly different to have completely different hash values. Right, so you can imagine here if we had two different keys that had the same hash and they try to get inserted into the same slot. But yeah, so anyway, we just have a running multiplier of 1, and then we multiply by 10 every time. So for example, like hashing apple, you can see here, it's the ASCII value of A times 1 plus the ASCII value of P times 10 plus the ASCII value of P times 100, and so on. So we iterate through the characters in the string, and we just multiply the ASCII value by a running number. So anyway, so that's hash tables. And again, they are, people like them because they're a constant time operation for all those. But they are pretty limited in the types of data you can use them with. And yeah, Python dictionary uses a hash table, so that's how those work. Binary search tree, this is our grand finale, folks. Binary search tree basically uses a node with 2 subnodes each. So you can kind of think of it like a linked list, but it can go in 2 directions. So you can see here, right in the bottom left here, each node has a left and a right node. And then basically, anytime we want to insert a value, we just have to basically insert the node depending on whether the current value, the value that we want to insert is less than the current node's value. So over here on the right, here's our insert function. If the root's none, we just make the root equal to our node. Otherwise, we recursively insert the node. So the recursive method, we check if our current node's value is less than the node we want to insert. And if it is, then we insert it on the right. If there is no node there, and if it isn't, we recurse on the right node. And then we can check otherwise we check if the left node's none, and if it is, then we set it on the left node, otherwise we recurse on the left side. So you can kind of see here, right? So 3 is on the left because it's less than h, 1 is on the left because it's less than 3, and then 6 is on the right because it's greater than 3. So you can really see that 6 is less than 8, 7 is less than 8, 4 is less than 8. So it's actually, the order is very specific. And yeah, so these are useful because inserting, access, and removing are all O of log n. And you can kind of see that if you have n nodes and each splits, you'll have log n levels. Okay. So just some quick review. Do you have some time for questions? So O of 1, constant time, like a random element. O of log n is log time, which is like binary search. O of n is linear time, which is like our average function, linear search, Fibonacci, iterative. O of n log n, which is called log linear time. That's like quicksort. O of n squared is quadratic time, so that's like common elements, bubble sort, selection sort, and insertion sort. O of 2 to the n is exponential time, so that's like our recursive Fibonacci function. O of n factorial is factorial time, that's like our traveling salesperson. And O of n times n factorial, I don't think there's a name, but that's what Boga sort is. And then here's a quick little chart of the algorithms, the data structures that we looked at. So you can see arrays, access, is an O of 1, but it's a little bit slower on the insert, search and remove. Hash table is just a constant O of 1, and then binary search tree is O of log n. Last slide, there's a couple of nice links there for you. The Big O cheat sheet is a great website. It just lays out the complexity of different algorithms here. And very nice charts. They even have a little infograph. This site's awesome, actually. I just discovered this today. Visualgo. It's just like a whole bunch of algorithms visualized, which I think is really great for understanding them. Wikipedia article is always good, and that's like a little online course. Okay. So I'm gonna stop sharing. All right, that was a lot. I'm sorry, it was an hour. I wanted to just kind of share a whole bunch of information with y'all. I don't know if I want to be spotlighted like this. Okay. Any questions? Really? Okay. Y'all are shy. I know there's 1,000 people in here. What's up, Dylan?
I got a question. Maybe not as much of a question as much as binary search tree seems intimidating. I would like to learn more about it. Mm-hmm. Question mark.
Oh.
Yeah, I don't have a specific question for it. I just like, yeah.
Yeah, those data structures they're really fun to work with. And there's another question in the chat. Do you feel like Big O is important for web dev jobs as it is for software engineer jobs? I would probably say no. I don't think it's probably quite as important for web dev jobs, just because web devs involves, there's a lot of design on the front end. There's a lot of database interaction on the back end. And oftentimes interviewers are just looking for proficiency rather than like, theory, because it is very theory heavy. But you are likely to find kind of algorithms questions in any tech interview. So it really depends, but you'll probably encounter it out there. And anyway, it's underlying everything we do anyway. Computer science it's the foundation of all computer technology. So it's out there. It's definitely worth knowing about. Cool. Any other questions? All right. Well, I don't know what to say. Algorithms are super fun. There's plenty of code over there in the code repository for y'all to play around with. The link's in the Zoom chat. And thanks everybody for coming. Sherry, did you want to say anything? You're muted.
Matthew, for taking the time to do this.
Oh yeah, of course.
I thought it was a really great overview, and I'm the least technical person at Code Guild, and even less technical than that. And I could understand some things. So thank you everyone for coming. I hope it was helpful to you too, even if you need to go back through the videos and rewatch it piece by piece.
Yeah, we'll upload the video to YouTube and we'll post it around.
We'll put the link on the meetup page. And then there's another one in 2 weeks on
Merit's doing advanced Git.
Right.
I'm excited for it.
Yeah. So thank you, Matthew. Thank you everyone for coming.
Yeah. Thanks for coming, everybody.
Bye.
Thank you.
Have a good rest of your night.